Welcome everyone to our fourth and last press conference today here at the European Geosciences Union 2018 General Assembly. And this press conference is organized in collaboration with NASA because it is on the latest results from the NASA JUNO mission at Jupiter. We have 5 panelists talking today, and there is a press release available online that NASA distributed, and it's also available at media.egu.eu/documents if you want to check that. And I'll introduce our speakers, and then I'll hand over to them. They'll speak, the 5 of them in a row, and then at the end, we'll open the floor for questions from the journalists here in the room and those watching us remotely via the web stream link that we have available. And the speakers are, so Scott Bolton is the JUNO Principal Investigator and is based at the Southwest Research Institute in San Antonio in Texas, and he'll be our first speaker. And then there will be Alberto Adriani, who is JUNO's co-investigator, and he's based at the Institute for Space Astrophysics and Planetology in Rome, in Italy. And then we will have Jack Connerny. He's a JUNO Deputy Principal Investigator and lead for the mission's magnetic field investigation, and is at the Space Research Corporation of Annapolis in the US. And then we will have, I'll just double check this, Tristan Guillot is a JUNO co-investigator from the Université Côte d'Azur in Nice, in France. And finally, at the end, we will have Steve Levin, who is the JUNO project scientist, and he's at the NASA's Jet Propulsion Lab in Pasadena, California. Now I'll hand over to our speakers now. Thank you.
Barbara, just before we start, could I ask whether the visuals are going to be made available?
So the visuals are made available through the press release, so there should be a link in the press release for them.
Okay, thank you, Barbara. So I'm Scott Bolton. I'm the PI for JUNO, and I'm going to go through and sort of run this briefing a little bit from the computer. You're going to find out immediately that I'm not a hardware person. So please be patient as I try to bounce between this. We're going to show some films and movies that we have from JUNO, and we couldn't do them inside the PowerPoint, so I'm going to kind of move around a little bit in the presentation. So here the first slide just shows you a picture of Jupiter and what the spacecraft looks like. And for those of you that aren't familiar with JUNO, we're a solar-powered spacecraft that's orbiting Jupiter. We're going over the poles. We're in what's called a polar orbit. One side of that polar orbit goes very, very close to Jupiter, just a couple thousand kilometers above the cloud tops. The other side, it takes 53 days to go out, so we go pretty far away. And then every 53 days, we come screaming by over the poles, getting really close. And almost all the data you're going to see today, and most of the data that's presented at the meeting, comes from that very close-in region when we're going right over the poles and coming down across Jupiter. And we go really fast. It takes only about 2 hours. This whole spacecraft is solar-powered. Each one of those arrays is about 8.5 meters long, which makes it one of the largest spacecraft ever built. And it cartwheels through space. So as we're traveling through and going by Jupiter, this whole spacecraft is spinning twice per minute, and the observations are made with instruments that are sticking out and looking between the solar arrays. And so that gives you an idea how it works. Okay, so there's just the first slide for me. And what I'm going to do is point out to you some of the beautiful images that we've gotten. We have a JUNO camera, a JUNO cam it's called, is the camera on board, the color camera. One of the unique things about that color camera is we take all the data and we post it raw right on our websites. And so almost all the images that we're going to show you are actually made by amateurs, students, people that go onto the website, learn and dedicate themselves to making a picture, and then we allow them to post that picture up. And so you'll see some very beautiful pictures, but also some that are sort of artistic as well as scientific. And some of the things the pictures are going to link to are some of the science that we're going to discuss across today from the different speakers. We'll do a little bit of stuff that's over the poles, and Alberto will talk about the polar cyclones, and I'll show you a few pictures of those from the visible, and then he's going to show it to you from the infrared perspective. And then Tristan is going to talk a little bit about the interior and what we've learned from the gravity field of Jupiter. Jack Connerny will talk about the magnetic field, so these are 2 invisible force fields that we learn about the interior of Jupiter from. And then Steve Levin will talk about another kind of observation that also looks inside of Jupiter using microwave, and there we look into the deep atmosphere All of Jupiter is a giant ball of gas, but the top layer of the atmosphere goes down several hundred kilometers. So these are 3 different ways to look inside of Jupiter, and that's really what the press conference is about, plus the poles. Okay, so the first picture I wanted to show is this one, which is just a really beautiful rendering, which just was released not too long ago, and you can see how beautiful and almost artistic Jupiter is in this. Now, this particular amateur that made this image applied something that was sort of artistic to it, almost like brush strokes, and what you see is it looks 3-dimensional. So that was the way that they interpreted it and wanted to publish it. The reason I'm showing this is it gives you an idea. There's no doubt that Jupiter's atmosphere really is 3-dimensional, and there are parts of the atmosphere that are above other things, clouds. We can see some cloud layers that are casting shadows. In this case, it's a little bit more of an artistic expression. However, when Alberto gets up to show you, he's taking data that's infrared, which means it's measuring heat, and the temperature of Jupiter's atmosphere changes as we drop down. It's higher up, it's at one temperature, and as we drop down, it gets warmer. And so there we actually have real data that can show you this 3-dimensional effect. And so what he's going to show you is an image that's actually made from the scientific data. This is more of an artistic expression, but it is nevertheless probably representative of real. These cyclones that you see in all storms, kind of like they are at the Earth, are more like funnel clouds. You know, there's something high up and then it drops down. And Steve will show something as well about the depth of the Great Red Spot, which is real as well. And so we've made these measurements. Here's one of the more beautiful pictures of the poles. This is sort of a distant shot, but you can see some of the polar cyclones. This particular person decided to sort of express their artistic sense by putting in these different colors. But in fact, the stripe across the middle is almost true color. It is kind of bluish, and it shows some of these cyclones going around the polar regions. Another closer picture shows you some of the cyclones up close. You can, I think, see sort of the why people do make artistic versions of these pictures, because Jupiter looks like a palette or a painting all by itself. But I want to point out that you'll see some of these very distinct white clouds at the tops of some of these storms. And these are some of the hints that we have of altitude, because we can see the shadows that those clouds are casting. And from that, we can calculate the altitude as well as the size. So some of these big white regions, especially the one that's sort of down on the lower left-hand side, right-hand side, is actually where we think a lot of lightning and thunderstorms are occurring. These other smaller ones may be pieces of ammonia ice clouds. It may be places where snow or hail is forming on Jupiter start to form down. Another picture is just a series of different polar shots. These are time sequence, so you can start to detect a little bit of change, although a lot of it is from the spacecraft change. But again, if you look close at some of these, you see some of the storms that are very geometrically distributed, as well as some of the polar cyclones. Keep in mind about this geometry, because when Alberto gets up to show you the next one, he's going to show you very, very geometric spaced polar cyclones that were a big surprise to us. Okay, so next I'll turn it over to Alberto.
Okay, thank you, Scott. I'm the responsible for one of the remote sensing instruments of the payload of the JUNO mission, and our instrument is called Jovian Infrared Auroral Mapper. It was built to get measurement about auroras and also about the atmosphere, but the shallow part of the atmosphere. So we are working in the infrared, so we cannot go very deep in the atmosphere, and the signal we measure actually is modulated by the clouds. They are on the shallow part of the atmosphere. And as Scott mentioned, one of the great advantages of this mission is to have polar orbits. So the poles were never observed before, both from Earth and both from other space missions, because all the other space missions moved mostly around the equatorial plane. In this case, actually, we flew above. Can you give us the first picture? Slide. Yes. we flew above the poles. This is in this picture here. This is the North Pole, and what we measure here actually is the heat coming out of the atmosphere. So we don't have as the camera as the problem that to have a source of light to see the clouds, because they need the sun. But we don't need the sun because the planet itself is radiating out this infrared radiation. As you can see here, we have this very structured cyclonic structure here. There are 8 cyclones. They are quite big. They are actually about 4,000 kilometers each. The diameter of each one, 4,000, between 4,000, 4,600 kilometers, more or less. And this is the South Pole is quite similar, but it's in some ways different, because here you see 8 cyclones around the polar cyclone, which is the darker one, and more clouds in the center of this structure. And the South Pole actually has only 5 cyclones around the polar cyclone. But the cyclones in the South Pole are actually bigger, much bigger than these ones. So they have more space to keep, to use on all this structure actually is inside about 10 degrees latitude around the pole, around the North Pole, and also around the South Pole. You won't see the South Pole here, but it's published on Nature, so you can see from there. So, and from this picture, you see the light, the bright areas there where you can see very deeper in the atmosphere, because we see the heat, less clouds, we see deeper in the atmosphere. And where we have clouds, it's darker. So this is actually a measurement of the temperature in some way. The temperature is not the actual temperature in that profile of the temperature in the atmosphere, but the temperature that the instrument sees. You imagine the planet as a black body, and if you give you a measurement of temperature from the black body, actually the bright spots are around minus 13 degrees Celsius, and the darkest areas around minus 83 Celsius. So it's quite hot. There's a lot of energy coming out of this planet. So now we are studying this. We are going deeper, studying inside where we can go through and go deeper, and we are studying the dynamics of these structures to understand how the atmosphere of Jupiter works. I don't know.
You ready for the?
Now I can show you a movie. This is a flyby. It's made of that, in principle, using those images, the images we got, putting together, give them a three-dimensional shape, using the temperature, using the optical depth. We will fly over the North Pole. Okay, thank you. I don't need to comment this. It's quite impressive.
Now you find out I don't really know what I'm doing. Okay, so how do I get out of this? Escape. I think escape might have worked. Right. Let's try to do it that way and go back to this. Okay, that went better than I thought. Okay, so Tristan is next up.
Okay, so we're gonna switch gears a little bit here because I'm gonna describe the investigation of the gravity field of Jupiter with JUNO. And you know the gravity field is invisible, so I'm gonna present some boring scientific graphs afterwards. But so we published last month 3 Nature papers, in addition to Adriano's very nice paper on the infrared data, because with JUNO we've been able to solve the very important question, which was if you have a big gaseous planet like Jupiter in space, how does it rotate? It doesn't have a surface like the Earth, and so it's not obvious at all what it's going to do inside. We know that Jupiter has zones and belts, as we can see here. They rotate at different speeds, and we didn't know what would happen inside of the planet. And now we've been able to measure that these zones and belts go down 3,000 kilometers deep. First, I'm going to show some graphs that look at the gravity measurements that we did, and I'm going to pick up 2 numbers which are called J4 and J6, and basically they measure how oblate the planet is. Jupiter is rotating rapidly, so its poles are its polar radius is smaller than its equatorial radius. It's a little bit flattened, and we're measuring that in the gravity field with all the anomalies. So we can see in the next slide, so this is one of these boring plots, but showing the different measurements that we had prior to JUNO. So you can see one, the purple one from 1985 that goes back from Pioneer and Voyager data, and then with Cassini and then with New Horizon we got a little better data, and so we have 2 other arrows that are discrepant with each other, and so we were really wondering what we would get with JUNO. And so in the next slide, I'm showing the point from our first passage. You can see there that the increase in accuracy is already enormous, and we were, from the first pass of JUNO, able to resolve this discrepancy between the 2003 and 2011 data. But now we're now at 11 passes, 11 flybys of Jupiter, we have an even better accuracy. And so that's on the next slide. You can see the yellow square there shows the really fantastic gain in precision that we were able to reach thanks to JUNO. And it's thanks to that we were able to really look better at Jupiter's interior rotation. But what we're after, and we're actually working on that, is really getting the composition of Jupiter. So in the next slide, I'm showing you an ensemble of models that we're getting, and you can see that they're going through the JUNO point. So the game now is to look really in fine details at these models, really in this fine yellow area, to what are these characteristics, what's the core mass in Jupiter, what's the global composition of the planet, and things like that. But it's something that is just starting, because up to now we needed to solve this problem of how Jupiter is rotating. And in the next slide, I'll show the uncertainty that we had due to the unknown interior rotation. Now, thanks to these 3 papers that we just published last month, we were able to solve for that problem and that uncertainty. And we believe we understand what's going on in the planet. And so the next step is really to look in finer detail at the composition of the planet. So the next slide will show what globally we obtained, and this is something that hadn't been released so far. There's also a movie that was released with the Nature papers. This slide is showing the zones and belts with different velocities, and the extension is in the of these zones and belts is 3,000 kilometers deep. So it's quite deep compared to our own atmosphere, but for Jupiter, which is 140,000 kilometers in diameter, it's a thin shell. And what's happening deeper down is that the conductivity of hydrogen increases. Maybe you can hit the space bar. And the magnetic field, the very powerful magnetic field of Jupiter, is dragging the interior into uniform rotation. We know that this magnetic field is generated somewhere in the metallic hydrogen region, which is this light blue area inside of the planet. And so that's why we're measuring that interior rotation is nearly uniform, and that we have a zone and belt structure with alternating speeds that's limited to about 3,000 kilometers. So that's something really important. It has consequences for Saturn, for example, for brown dwarfs and exoplanets. And I would say more importantly, now it allows us to continue working really on the composition of the planet itself, getting its core mass and getting the abundance of heavy elements in the planet. So that's it.
Okay, next up is Jack.
Thank you, Tristan. So it's my job to talk about the magnetic field and the results from this first part of the JUNO mission. Tristan was challenged to talk to you about gravity, but at least we all understand that gravity keeps us in our seats. Magnetic fields are even more abstract, but if you envision a bar magnet, planets generate their own magnetic fields by what we call dynamo action deep inside the planet. In the case of the Earth, the dynamo is down about halfway to the center of the Earth, and it is generated in electrically conducting fluid that is in convective motion. But the Earth is the only example we have of a dynamo. And so while we understand intuitively how you can generate a self-sustaining magnetic field, we don't really know the details of how that happens. So it's very important to have another example. And JUNO is providing now us with the first other example of a planetary dynamo. The magnetometer experiment, if you look at the spacecraft here, we use two instruments, magnetic field sensors, out on the pointy end of that solar array that you see. And we measure the magnetic field throughout each of our orbits. And as Scott mentioned, our orbits go from pole to pole. We're the first spacecraft to do that. All other spacecraft to the Jovian system have been in the equator plane, and so they haven't had that entire third dimension to explore. We're doing that for the first time, and that provides a tremendous advantage in our ability to characterize the magnetic field. That and the fact that we get so very, very close to the planet. So I want you to think about a bar magnet and put that at the center of the planet and a magnetic field. If you remember in elementary school when they sprinkled iron filings on that bar magnet, that's what the magnetic field would look like. And in the case of the Earth, it sort of looks like a bar magnet. And what we're going to do here is put on some special glasses that allow us to see magnetic fields. We're going to color code positive radial magnetic fields, the kind that come out of one hemisphere, red if they're positive, and we'll color code them blue if they're negative. So when you see the red, field lines are coming out, and when you see the blue, field lines are going in. Now we'll go through and start this animation here.
The movie, right?
So we start here with Jupiter as it appears to our eyes. We see the belts and zones that Tristan was just mentioning to you. And we'll start with the belts and zones, and then we'll put our special glasses on, and we'll see what the magnetic field looks like after 8 orbits. The magnetic field appears here. You see a band of positive radial field encircling the planet at the equator, interrupted by a negative patch at about 90 degrees longitude. Otherwise, the equator is sitting with a positive radial field. The southern hemisphere is quite dipolar. It's very uniform. The northern hemisphere, in contrast, has a lot of positive flux coming out at around northern mid-latitudes, around 45, 50 degrees. And it's also the site of a lot of anomalies, we call them. You can think of it as a patchiness in the magnetic field. And here we're sort of looking below the surface to where we think the dynamo might be generated. So there's an extraordinary hemispherical asymmetry to the magnetic field, which is to say that the northern hemisphere looks remarkably different from the southern hemisphere. And this was totally unexpected, of course. And if you looked at the Earth's magnetic field in a similar way, you would find nothing to distinguish the northern hemisphere from the southern hemisphere. And so for a fluid planet, this is going to be a challenge for some of my dynamo friends to try to understand. But of course, in the challenge, there's an opportunity to advance what you know about dynamos. So this is going to be a very critical piece in understanding how a planet actually generates its magnetic field. Now, we are only a quarter of the way. We can go to the next slide. This result was published last month in a journal called Geophysical Research Letters, and it represents just the first 8 of our planned baseline 34 orbits. In our potential field, one gets an image or a view of what the magnetic field looks like by being there and measuring it in situ. And your resolution depends on the observations that you have, the coverage that you have of the planet. And this illustrates the coverage that we will ultimately achieve when we have all 84 of our closed perijove passes. And so while we see the field now with a kind of an out-of-focus view, that focus will improve as we collect more orbits. I think we have one more. And so here's the boring slide, not to be outdone by my colleague Tristan Guillot. And this slide shows you the amplitude as a function of harmonic degree. Think of harmonic degree as a spatial scale. As you get higher in harmonic degree, the spatial scale shrinks. Now for the Earth, with satellites over the past 50 years or so, we've mapped that magnetic field very accurately. And the decrease in the amplitude as a function of spatial scale, their harmonic degree, tells you how deep inside the Earth the dynamo operates at. And that's how we know it's down at about 0.5 radius. In the case of Jupiter, before Juno, we only had the first 3 squares in the upper left-hand part of that plot. And now we've gone to degree 10. We've added considerably to our knowledge. And you see those squares are falling pretty much between our predicts of a dynamo radius at 3/4 of the planet radius to maybe 0.85. Now, as we get more and more orbits and approach the end of our baseline mission, we're going to creep down that curve on the right-hand side, and eventually we'll have a better view of what the field looks like at the surface of a dynamo than we would ever have by measuring it in orbit about the Earth. Because in the case of the Earth, the crustal field, the magnetized matter beneath our feet, introduces noise, and it obscures our view of the dynamo deep inside the Earth. So that's what we're looking forward to. But already we have now for the first time a second dynamo that is well described, that hopefully will help us understand how planets generate their fields. That's all for me.
Okay, next up is Steve.
So I'm going to talk about Juno's microwave radiometer and some of our results. You can go ahead and do the next slide right away. The 6-channel microwave radiometer on Juno peers beneath the clouds. We use radio waves so we can see a few hundred kilometers into Jupiter. And on the scale of Jupiter, that's thin, right? But that's much deeper than we've ever seen before to be able to actually look into the planet and see below the clouds. And what we saw when we first looked, for the first time ever below those clouds with the radiometer surprised us. We see this asymmetry that you can see there, as has been mentioned. North and south don't look the same. The belts and zones that you're seeing, the stripes, don't go down into the depth the way, they don't just follow down deep, but we do see deep structure in some places that goes hundreds of kilometers into the planet. So that's deeper than we thought. You get below the sunlight and the clouds. Before we got to Jupiter, the general consensus was that what we'd see with the radiometer would be pretty much uniform once you get below the depth of where the clouds and the sunlight reach. And that's not the case. We see structure as deep as we can see. If you go to the next slide, we now have 10 passes by Jupiter. And let's see if we can get the movie going. So now what we've done is taken that picture but spread it out so we have latitude across the bottom and depth at the top. And it's not playing.
This is the one we loaded externally. Either.
Maybe you need to be in presentation mode.
I'm not in the presentation mode.
Last one.
This one?
No,
That thing.
Well, we got to step through it.
Sorry about that.
All right, well, what you're going to see in that is that with successive passes by the planet and looking a few hundred kilometers below the surface, what we see changes each time. The basic structure is there. This is still not playing.
You have to right-click it, maybe. Not clicking.
Everybody that knows me is thinking, that's exactly what we expect from Scott.
Exactly.
So I apologize.
All right, well, maybe when we're done, I can bring it up on my computer or something. What you see is variation in structure where that big ammonia plume that we're seeing, that zone of ammonia near the equator is always present. The broad features of the structure are still there, but with successive passes by the planet looking at different longitudes, we see details in the structure that change. And as you can see, the belts and zones don't extend the same way, say, in the south as they do at the equator, and it looks different in the north. Why don't we go on to the next thing then? One of the features that we see that shows up clearly differently is on our 7th pass by the planet, we went over the Great Red Spot, so we were able to see that with the microwave radiometer. For the first time, we can get a measure of how deep the Great Red Spot goes, and the answer is it goes as deep as we can see. That was also a surprise. So down at as far down as 350 kilometers or so is about how far we're seeing with our deepest channel. We still see the Great Red Spot extended into the planet. And we were able to use that knowledge that we got from the microwave radiometer combined with the images we got from JUNO in the visible to make the movie, which I guess you now have to exit the thing and bring up.
Yeah, better.
This movie. So right. So what you're going to see is real JUNO images, and then as we penetrate below the surface, we use the microwave data to inform the artist impression that's shown of what it looks like underneath as you go in and see the temperature and depth of the Great Red Spot. I think that's the last thing in our... Yeah.
I think that's the end, but I'll hit slide to current window. No, it's this thing. That was the end. Okay, thank you.
Thank you very much for your presentations. We'll now open the floor for questions. Are there any questions from the journalists here in the room?
Jonathan Amos, BBC. Alberto, can I just confirm the temperatures you were saying? So the dark areas, they're cooler, yes?
Cooler, yes.
Yeah.
Cloud thicker clouds.
Yeah. So that's minus 83 Celsius, is that what you were
Yeah,
saying?
it's the apparent temperature we measure, yes.
Yeah, and then the lighter areas is minus 13.
Yeah.
Yeah, absolutely. Yeah. Have you ever been to Cambridge, to Fitzbilly's, the cafe? Very famous Cambridge cafe.
I've gone there.
You've been there? They serve what's called a Chelsea bun. Have you ever seen a Chelsea bun?
know.
If you see a Chelsea bun, you'll recognize Jupiter. It looks exactly like that.
Exactly the same.
An amazing pastry. Here we go.
So whoever figured that out had a vision.
Andy Coglan, New Scientist. You've got lots and lots of Perry-Joves to go. What sort of highlights are you looking forward to in the future? You must know roughly what you're going to be looking at in the future. So what can we look forward to finding out next?
So I'll give a high-level one, and then people can chime in with their own science. But so we're about a third of the way through the mapping phase, and what we're going to keep investigating in the remaining orbits is we're going to get a finer resolution of the magnetic field, right, which is really going to help us understand where we go on that curve that Jack showed, and help us understand the dynamo. But it's also going to help us understand roughly how deep where the magnetic field really forms. And that's an important question, because the transition region that Tristan was talking about between the places where Jupiter's rotating with flows that are similar to what we see in the zones and belts versus deeper down where we think somewhere around 5,000 kilometers maybe or so, it's moving as a rigid sort of a uniform body. That transition region isn't well understood, or how that works. Some theories suggest that maybe it's tied to where the magnetic field starts to become more important. Also, what's creating these zones and belts, or these eddies and jet streams that we see. So as we dissect and get more gravity passes, we'll understand that transition region, and also be able to confirm or constrain the idea of whether there's a small compact core underneath this larger diffuse core. We also, of course, we want to monitor these polar cyclones that Jerome has discovered. They're really puzzling, and one of the first questions is, how long are they lasting? Are they stable? Why don't they merge? Are they like the Great Red Spot, that they just kind of sit there and swirl around but last a really long time? Or are they going to be more like a weather pattern where maybe they should merge or kind of eat each other and sort of evolve? And so the remaining of the mission, as we go over with that instrument, we'll be looking closely to try to understand the motion and the dynamics associated with that. The microwave, our orbit changes as we go more and more times around, because of the fact that Jupiter's gravity field is not perfectly symmetric. As Tristan pointed out, it's fatter at the middle than it is at the poles. It's oblate. That kind of difference from a perfectly spherical, single point gravity field makes our orbit twist around. At first, we kind of wanted to stop that, and it was going to take a lot of fuel. But it turns out that that's a scientific advantage, because as that orbit twists around, literally the part that's where we're passing very close to Jupiter moves further and further north, which means toward the latter half of the mission, and even toward the last quarter of it, we're much closer to the poles than we were at the beginning. And so one of the big puzzles we have with the microwave that Steve showed you, you only saw a map that went out to plus or minus 40 degrees latitude, because when we got over the poles, the picture that we had, sort of the resolution was very weak, right? Because we're really far away. So as we get closer, we're going to be able to extend that map to the polar regions. And that's a big question because we don't understand why the equator is different than the mid-latitudes. And then now we see all these polar cyclones. What is the microwave going to tell us about that polar region? It's probably brand new. And so rather than make a prediction as what I think we'll see, because so far very few predictions have been right, so I've become more cautious, especially mine, yes. We'll discover, what's underneath those polar cyclones, which will help us a lot. And as Tristan also pointed out, one of our key scientific objectives is to get the global abundances, the composition, which is really going to help you in the interior structure. And so we'll see if the polar composition is different than the mid and equatorial regions, mid-latitude and equatorial regions, because what we're really after is what's the total composition. So you have to average it all and look everywhere. So that in a nutshell is some of the things. Now, what I've left off is a part of the science that isn't really discussed a lot in this particular panel, and that is the exploration of the magnetosphere and the polar magnetosphere, and particularly the aurora. So there's a few papers on the aurora here as well. The northern lights of Jupiter, of course, the northern and southern lights is what we're interested in, and we're passing by learning about that. And one of the things that we will do in the remaining part of the mission is we will explore new territory in Jupiter's magnetosphere, which is very important and will teach us a lot about how the magnetosphere works at Jupiter, because it's a very large object, in fact. If you look at the size of the Jupiter's magnetosphere, it's actually the largest object in the solar system because the tail reaches out past Saturn. I mean, it's quite large. And learning about that dynamics, we'll also learn about the radiation belts, which are really important. And at the end of the missions, we'll be going through regions that are very pertinent to JUICE, the ESA mission that's going to visit Ganymede and Jupiter following us, as well as U.S. Europa Clipper mission. And so we'll learn about the radiation belts and give them sort of a warning. Anybody want to add some stuff?
Yeah, let me just expand on that a little bit. When you're measuring a potential field, your resolution, your vision, depends on how far apart your observations are. And right now, with 8 orbits, we're separated by 45 degrees from each perijove. So that's 8/10 of a planet radius. Now, we're only this far from the source, which is about 1 to 2/10 of a planet radius beneath us. And ideally, what you want to do is gather your observations no further apart than you are above the source. So I see you're wearing glasses. So there's a good analogy here. When you go to the optometrist and you look at that chart on the wall, and they put in a bunch of diopters so it's really fuzzy, that's what we see now. And as we get more and more orbits, they're dropping in these diopters to correct your vision. So when you look at a tree, it's not a big blob of green, but you actually see leaves. So that's what we're going to do. We're going to look for the leaves.
So as
Marlo Hood with Agence France Presse. Question for you, Alberto, which I think Scott has maybe largely answered. But the sort of remarkable images we saw of the North Pole, my question is how stable that is. So just based on the number of passes you've made so far, what is your sense of that? And what is the atmosphere composed of at that point?
So the stability, we actually, because of the orbit of the spacecraft, we had very good observation of the North Pole at the beginning of the mission. We are now going to have many good measurements of the North Pole later in the mission, because the attitude is different position of the sun, so the situation is quite complicated. But we can monitor practically every orbit South Pole, because we are moving out South Pole, so we can keep track of the movement of the South Pole. So far, we had some measurements. We had those measurements at North Pole. We have other measurements, some stripes, say not complete like those. But we can say from what we saw so far, North Pole is very stable so far. I mean, And there is a lot of wind blowing inside the cyclones. The winds going up to 350 kilometers in some cases inside the cyclone. But the cyclones don't move. Practically they are stable, quite stable. We saw that the cloudiness changed a little bit, but not very much. The structure, you've seen some of them, they are quite ordered. So the clouds are not very patchy, they are quite well spiraling around the center. Others are very patchy, very many clouds. They stay like that for a long time. The same we see in the South Pole. We can have the view of the South Pole, complete view of the South Pole. While North Pole is very stable, we didn't see any movement so far. Actually, South Pole is moving a little bit, but it's moving, all the structure is moving. You can imagine the structure, because the structure of South Pole is not very centered on the pole. It's a little bit off the pole. You can imagine this pentagon with the center of the cyclone, something frozen, more or less. It doesn't turn like this, but it moves altogether, a little bit, not very much. So that's yeah. The clouds, what we see, mostly the clouds, they are not very shallow clouds, what we see. We expect that they are about 2 bars, a little bit lower in the atmosphere. So we see lower than the camera that see the higher clouds. Because the particles, the air clouds are small, and so we are not very sensitive. So the bigger clouds, lower, are thicker, and they can actually change quite significantly the amount of it we can measure. So we see better those clouds. We see also the upper ones, but not so well. That's what we can see. And I don't know if I answer everything. The composition is, the name is, I mean, the higher clouds should be made by ammonia mostly, and the lower clouds are made by a substance that is mostly, has nitrogen inside, water, ammonia, and nitrogen inside. It's the clouds, we expect that the higher clouds are covered by sort of soot around, something like that. So it's complicated. These droplets are small but complicated. This is what actually the retrieval from our models tells us. So because we have models that we can actually looking at the emission of the planet between, let's say 4 and 5 microns, where we can see with the spectrometers, because the spectrometers permit us to go down, where there are not many clouds, because if there are many clouds, we don't see much. But where it's clear, in the bright spots over there, actually we have looked inside, we are looking inside. We see that mostly we can measure water, say the humidity practically, and also ammonia quantity of ammonia. That is more or less that we see MWR on top, like that. And that's the kind of the compounds we can see. We can also have an idea of the phosphine, which is another molecule, which is very similar to ammonia, but has a phosphorus instead of nitrogen there. And that is some indicative of the motion, vertical motion in the atmosphere, because the phosphine is created down in the atmosphere, and when it's moved up, actually the sun probably destroys it. So it's give us some idea about this. This is what we can measure with our measurement, with our instrument, actually.
This is a question from the live web stream asked by Harvey Leifert, who's freelance. And this is a question for Tristan. He says, what have you determined is the period of Jupiter's axial rotation?
What is the period of?
The period of the axial rotation?
9 hours and 55 minutes. That's measured from the gravity field of the planet. It's very stable and very accurate. And then we have these about 1–2% variation in the atmosphere in zones and belts that can rotate faster or slower than the magnetic field.
Thank you. I think we have time for maybe one more question.
Hi, yes. Just to return to the dynamo. So this activity we think is what at least 10,000 kilometers down, basically. So down below the 3,000, which you were talking, where we've got a lot of sort of east-west activity, down into the layer where everything goes together, and that dynamo, there's some sort of convection, some sort of fluid motion in the metallic hydrogen, then is presumably generating this enormous field, 10,000 or more kilometers down. Yeah.
I mean, the thought is that the magnetic field itself is enforcing the rigid rotation of the deep atmosphere, and only when you get so high up, when the electrical conductivity shrinks to a negligible value, then you can have differential rotation. But if you go much below that 3,000 kilometers, the conductivity increases very rapidly, and that allows the magnetic field to hold on to the fluid, and it won't let it slip. So the thinking is now that we have rigid rotation at that level in the atmosphere, enforced by the magnetic field.
How much stronger is that planet's magnetic field compared to ours?
In apples to apples comparison, it's 20,000 times stronger than the Earth's magnetic field. But of course, the magnetic field decreases as you get away from the object. And Jupiter is a very, very large object. So by the time you get to the surface, the magnetic field is only about 20 times what the field is on the surface of the Earth.
Right. But it still has the power to drive all of these particles and everything when it interacts with the stuff coming off the sun. Right.
A question for Jack, and excuse me if you just answered this and I didn't understand it, but what's your best guess now as to the explanation for this unexpected asymmetry that you found?
I don't actually have a good guess. We're talking about a fluid planet, and at first blush, why would the one hemisphere behave differently from the other? So we're a little bit surprised by that. And that equatorial anomaly that I showed you in the video, that blue spot, has us scratching our heads because there's this circumferential band of positive flux, and then there's this one anomalous high field strength negative patch, which we're calling, by the way, the great blue spot, by analogy to the great red spot that you can see. Yes, this is all new. The first time our colleagues have seen this is a month ago, and it's going to take a little while to come up with some ideas, but I'm quite sure they'll have a good many of them.
Thank you. I think we are getting to the end of our time, so I will finish here. Thank you all very much for coming. Thank you very much for your presentation.
I just wanted to add one thing to clarify on the rotation period, that question that Tristan answered. So historically, we've measured the rotation period through the magnetic field. We've looked at radio emission. That's how you calculate Jupiter's inner rotation. I think you mentioned gravity field, and I'm gravity. And I think you meant to say magnetic. So I just wanted to, in case somebody's writing that.
He just wants to take credit for it.
So the rotation period is measured through the magnetic field, which is deep inside, and that's what why you think once it controls, that magnetic field is telling you what the deep inside of Jupiter is rotating around. It's possible the core is doing something different, but that would be a surprise.
Thank you very much. Okay, we'll finish here. Our next press conference is tomorrow at 11:30, and it's on what's at risk from coastal hazards. I hope to see you there. Thank you. Thank you.